Okay, so I'm going to call this a minimal, maybe, a minimal introduction to geometry of neural networks. Minimal in the sense I'm going to really talk about the most simple, non-trivial example of a neural network, which is the following. One input node, two hidden nodes, an output node, weights A, B, C, and D, no biases. So I'll basically be following what's in Spencer's thesis, which you can find. There's a link in the Discord. So here's the function. So if we suppose the target function, the true parameter, the true function is ft equals 0, then the KL divergence or loss is, let's take input space minus 1, 1. So that's the space that contains the x's, and I'll take the uniform distribution on that. Then the function that we care about is the integral over the input space. Well, it's the KL divergence, which for exponential models turns out to be given by this, which, if the function we're trying to approximate by this, 2 hidden node, 1 hidden layer tanh network, is the 0 function, that's just this. Dx. It's a bit awkward to have dx, isn't it? So that's our analytic function that we're trying to understand, and singular learning theory says that its geometry affects the process of learning that true parameter given this model, the model being the space. So W, the space of parameters, is some compact subset of R4. Okay, so theorem. We could cite Watanabe for this. So it's a bit of a, in some ways, a long story, but we've discussed this in other seminars, so I won't spend much time on it today. Excuse me. So there exist positive constants C1 and C2 such that K of W satisfies these inequalities, where HW is what we call the equivalent polynomial. And it is AB plus CD squared plus AB cubed plus CD cubed squared. I'm going to call this F1 and this F2. Okay, so what this pair of inequalities tells us is that in particular these two functions have the same RLCT. So if you perform the resolution and then compute the RLCT from the resolution, you can prove that both h and k determine the same numbers. So if we care about the RLCT of k, and we do, because that determines the generalization error of a model, which is using a neural network of this architecture, then we want to know the RLCT of k. To compute that directly is difficult, so we compute it by proving that it's the same as the RLCT of h, and then studying this polynomial, to which we can more easily apply techniques like blow-ups and so on. In particular, these inequalities tell us that the zero sets of h and k are the same. So W.
Sorry, Dan. Why did the square disappear in the second line on the first board for the k
thank you.
divergence?
Yeah, it shouldn't have disappeared.
Okay, cool.
Thanks.
Also, are you not attached to the speaker? Because it sounds like to me coming through just one side of my headphones. That could just be me.
Thanks, I'm not. Yeah, the iPad account is. I'll fix that.
Oh, that's much better, thank you.
Yeah. Okay, hopefully I should be coming from between your eyes now.
Yes, it's much better.
Great. So the zero set of k is the same as the zero set of h, which is the same as the vanishing set of this pair of polynomials f1, f2. So let's perform a little exercise of solving this pair of equations and having a look at the resulting affine variety in four-dimensional space. Okay, so to solve, AB plus CD equals 0, AB cubed plus CD cubed equals 0. Okay, well, from 1, get, I don't remember which pair you prioritized, Spencer, in your thesis. Maybe you replaced CD, or was it AB?
I think I replaced AB.
Yeah. Okay, we substitute into 2, which gives us, so that's ABB plus CDD is equal to 0. Gives us minus CDB plus CD squared is equal to 0. Therefore, CD D minus B is equal to 0. I feel like I'm missing a factor. What did I do wrong?
There's a CD cube.
Oh, it's cubed. Yeah, thanks. Yeah. Okay, and it was also... Right, so there's a B squared here, right? Okay. So I get CD minus B squared plus D squared. Okay, so I get CD, D minus B, D plus B is equal to 0. Okay, so now we're going to divide into cases, I guess. Well, so maybe, I don't know at what point to peek at the answer exactly, but this is going to be a union, this set W0 is going to be a union of irreducible components, each of which is a plane of some form, a hyperplane of some form. So we're not going to get us, there's cases in our future, is what I'm saying. All right, so let's, I suppose, start with a case where C is 0. If C is 0, then what does that tell us? Either A or B have to be 0, right? So A equals 0 and B is free, or A is free and B is 0. Okay, so that gives us 2 lines. Case 2. I actually forget which of these 4 variables, which one did you drop in the picture that I'm going to put up in a moment, Spencer?
I think I dropped D. Yeah.
Okay, so we will...
I think also in case 1 we also have that D is still free, so we end up with 2 planes.
Oh, that's right, yeah, thanks. So D is free. So case 2, these are not disjoint exactly, right? So D is 0, C is free, and same. Yeah, maybe let's already try and find them. I'll just put the picture up on the board. If I can remember which one is which, just a second. Not that one. Also another one. There we go. Okay. Guess we have enough symmetry that it almost doesn't matter which axes I pick to be which. So it's A, B, and C in some order. What have we found? We've found, so...
Yeah, that's not right. It matters which ones are input weights and which ones are output weights.
Yeah, that's true. Okay, we just found 2 planes. Can we locate them? D equals 0, that's a good one because we're going to project onto R3. So that will be A equals 0 and B is free. So those should be 2 lines, right, in the projection?
Yeah, I think so that red and blue line would be coming from case 1.
Right. So do you think this is A and that's B and that's C then?
Yeah, I think that would make sense. Yeah.
Okay, so that's B equals 0. Well, wait. But C is free. So, okay, let's look at case 2. This here will give us all the things of the form 0, anything, anything, 0. So if we just take these points.
Yeah.
Sorry, I don't mean to interrupt you, Dan.
Yeah.
Are you sure that you fixed D, the input weight, and not C, the output weight?
I'm pretty sure I think I projected D out. I can.
Because it just seems like the diagonals come from when B and D have a relationship. everything else is kind of axis aligned because it's like one of the things is 0. So in this picture, I'm seeing those diagonal planes maybe correspond to movement along the b equals d or b equals negative d line. But you can't have that movement if one of those is fixed. And also, when I plan to draw these plots, I plan to show that show the input weights and project out the output weights, because I think for the same reason, that's like the more interesting. Output weights are less interesting for this picture.
Yeah, I'm just trying to double check. Like what I've got written in my thesis is just that I've projected D out.
And is D definitely not like is Dan's letters the same as yours?
Yeah. That's the same. Yeah.
Okay.
But yeah, I see the point. Yeah, how... Okay, so what other cases will we have? We'll have one of those components has to be 0. So it's either C equals 0, D equals 0, D equals B, or D equals minus B. Can we go back and look at these? I mean, if D is B, then we get AB plus CB is equal to 0. So either B is 0 or A plus C is equal to 0. So we can get equations like that from here.
Okay.
So maybe we shouldn't have jumped to the picture. Maybe I should have finished the cases, and then we would have had a more symmetric story before we got started. So maybe let's do that. I'll take this picture off this board and finish the cases, and then we'll go back and see if we can understand the picture.
That's but the output weights. Yeah.
Okay, so case 3 is D equals B, and if D equals B, what happens to the rest of them? So AB plus CD equals 0 means AB plus CB equals 0. So B equals 0 or A equals minus C. Maybe there's more to say, but let's move on to D equals minus B, which will mean AB minus CB is equal to 0. So B equals 0 or A equals C. Okay, so the upshot is that W0 can be written as a union of, okay, which components? So just follow what Spencer wrote down in his thesis, and then we'll see if we can understand why. So he called that case, well, his cases are probably different to mine, are they? No, I think they're the same. Case 1 is C equals 0.
I think they're the same, yeah.
Yeah, well, that's good. So you said this was case 1. This was case 2. Three and 4. Okay, let's see if we understand why that is. So case 1, C equals 0, and if C is 0, then okay, so the union is an OR, right? So either A equals C equals 0, or b equals c equals 0. Yeah, that's right. For case 2, it's symmetric, right? So AD, BD, yep. Case 3, we have b minus d is 0 and a plus c is 0. What happened to the b equals 0?
It reduces back to one of the ones from case 1 or 2.
Right, yeah.
So if b is 0, then d is 0 as well.
Right, so this case here is part of the intersection of these two components.
Mm.
Okay, and similarly for the last one. Yeah, all right. So whenever we have an algebraic variety, it always has an irreducible decomposition. Irreducible meaning that it can't be written as a union of two smaller algebraic varieties. And if you take the components to not contain any of the other components, that decomposition is unique. And that's something you can do just at the level of sets once you have an expression like this. So, I mean, there's a kind of ideal theoretic presentation, which is called the primary decomposition. But we can already infer from what we're looking at here, as long as we believe none of these are they intersect each other, but as long as none of them are contained in each other, then yeah, I think that's right. Okay, shall we look at the picture? It's kind of awkward that we have to do it on a completely new board. But so yeah, please go ahead. I'm going to copy these components over so somebody else can start annotating while I'm doing that, because it's going to be a bit difficult to understand unless we have this decomposition also visible. Okay. A, B, C. Right, so what is yellow? Yellow is, you say, A equals C. This guy, right?
Yeah. So we'd have like A minus C.
And B is equal to minus D, and D is not in the picture. So when you project it, you just get... Let's maybe write this down. So take pi.
This is a slice when D equals what? Like just some fixed positive constant or something? Maybe 0? Not 0. It would be interesting.
So it's, I guess, like in R4, each of our points will have a B, C, and D component. This is just the projection onto the first three components.
Okay.
So D can be anything.
Right, so it's not a slice. Yeah. Okay.
Yeah.
Misunderstood that.
So what does something in here look like then? It looks like A, B minus B, and then we're projecting this out. So we get all the things of the form A, B, A, where A and B are real numbers. That's a plane. And yeah, that is the yellow thing. All right, good. What other colors can we get? So A equals 0, and c equals 0 gives us the red line, right? b equals 0 and c equals 0 gives us the blue line. Now, a equals d equals 0 gives us the purple stuff. B equals D equals 0 gives us the, whatever that is, teal. And then that leaves the pinkish plane, right? Don't really have that color. Okay, did we miss anything? So the image is pi of W0. Okay. A few things to notice about the picture. So this is a picture of a projection of the set of true parameters for our model, or the set of zeros for our loss. And the origin here is the most singular point, because it's where all these components meet. What else do we want to say?
It kind of looks like some of those components are in some of the others, so the lines. But is that just an artifact of the projection?
Yeah, I think so. Yeah, so when, in R4, I think they will be a bit different. Yeah.
So it's because the D component would let you walk around on those lines, but not on the planes that they look like they're inside.
Yeah, yeah.
Yeah, we would take this one here, which appears like it's contained inside this one. That's because if A and C are both 0, then A is equal to minus C, but you would have points like 0, 1, 0, 2, which lie in here but not in here. So that's yeah. So in R4, then they're not contained in each other.
Cool.
Alternatively,
I have a few observations.
Yeah, go ahead.
I'll add this to the next board. So the work that I was presenting last week on reducibility conditions kind of gives an alternative picture that would get you to this same conclusion. So I want to sort of sketch both pictures. So this KL divergence method, you start with the KL divergence equals 0 as your constraint, and then you calculate the equivalent polynomial.
Sorry to interrupt, Matt. Maybe you want to attach a speaker so the audio gets you straight on.
Sure.
Thanks.
There you go. So yeah, okay, so KL divergence equals 0, and then you go, we calculate the equivalent polynomial, and we say that is equal to 0, and then we just sort of look at the equivalent polynomial, reason about the cases to calculate this irreducible decomposition of the, if I call the equivalent polynomial P, the variety of P, the 0 set. That's what we just did. The approach that my work has used just starts with the constraint that the two parameters need to be functionally equivalent. So that is the function you get when you try one set of A, B, C, D. We want that to be equal to the function that you get when you try another set. And we started with the assumption that the true parameter was 0, right? So I'm going to put 0, 0, 0, 0. And we want to see for what A, B, C, D is this the case. We apply, basically, if this was Watanabe, who calculates the equivalent polynomial for us, here we apply Sussman, who gives us conditions of reducibility plus my thesis, which iterates those conditions of reducibility to produce basically what we talked about last time, which is something like the reduce of A, B, C, D is equal to 0. And then that gives us this same set when we try and look at that. So this is like two different ways of getting a characterization of this set. Any comments on that so far?
Yeah, they look kind of equivalently difficult for the 2-neuron case somehow, but if I recall correctly, Spencer, once you go up to, say, even 3 neurons, it's not so easy looking at the polynomials to deduce these components, right? I mean, maybe it's not difficult, but there are some extra steps involved to actually extract this kind of information, right?
Yeah, that's right. Yeah, it becomes quite a bit more complicated, and that's where like the whole elimination theorem stuff came in. Whereas, the sort of reducibility conditions, I guess, they seem to sort of be much easier to apply when your networks are getting bigger and bigger.
Yeah, I wonder to what extent, I mean, you could think that there's more information in the algebraic thing at the end, even though it's more effort, because it does tell you the reducibility approach in principle seems to only tell you where the KL divergence is 0. It doesn't tell you what the function looks like near those zeros.
I would agree. I would say that the equivalent polynomial is like a heavier result than Sussman's reducibility conditions because of that, exactly that. But I would... sorry, Spencer?
I think one other reason we went with the polynomial approach in my thesis, like, I guess partly because the whole thesis was about polynomials, but also we were speculating maybe like this whole equivalent polynomial stuff works with other types of networks, like deeper ones, where it's not clear, like it's clear whether like there'd be those reducibility conditions.
Although maybe, Matt, you think that also should work?
Well, okay, so my perspective on that would be that while Watanabe's equivalent polynomial is a heavier result because it has this sort of neighboring information as well compared to Sussman's, I would say that from this point, these two approaches are doing the same thing. And so when I have in my mind the reducibility concept and these algorithms for computing this reduction, that means that I could come to a larger version of the equivalent polynomial for a larger network, and I could tell you what the irreducible decomposition is based on sort of my intuitive guess of it, based on my understanding of the different ways that networks can kind of combine and reduce. Units, can combine and reduce. So I'd say this is doing the same thing from that point. I would say that you could probably get reducibility conditions in other networks, just like you could probably get equivalent polynomials in other networks. I would say that's probably similar. But like I said, Watanabe's result is kind of heavier because it's also got this extra information. That's what we want in the end because we want RLCTs. But If you only wanted this 0 set, then I think you could do it with either approach, and maybe one or the other would be more straightforward. And once you cross this line, then you kind of want to use both to be able to have the intuition and also the polynomial description of it. It's just like an extra description of it.
Yeah, makes sense. Maybe there's some low-hanging fruit here we should just stop and pick. So let's go back to this this image, if you don't mind me taking over the orb again, Matt.
Go for it. I'll have to drop it, right?
Yeah.
Just give me 1 second.
So let's go back to this picture and, well, maybe all the way back to the polynomial itself, h. Okay, so h is ab plus cd squared plus ab cubed plus cd cubed all squared. Okay, what is the largest degree that has with respect to any given variable? Well, it's the b cubed squared, right? So there's a 6th power there. But if you lie on the subset of W0 where a is equal to b, for example, then that will go up from the 6th power to the 8th power. So roughly speaking, the very crudest way to think about the RLCT is that it's 1 over the power, right? So the RLCT of x to the 10 is 1/10, something like that. So if you have a polynomial that's increasing in degree, it's more singular and the RLCT will be smaller. So if we go back to this diagram, then I'm just going to think at a very rough level, very heuristically, about where the RLCT is smaller and how to read that off from the picture. Okay, so out here, say, the only equation we have is that a is equal to minus c. So that means at this point, h looks something like, so a is c, so that's ab minus ad squared plus ab cubed minus ad cubed squared so that's a squared b minus d squared plus a squared b cubed minus d cubed all squared. If we then move from here to here, so the red component was where a is equal to 0 is equal to c, right? Then h becomes at that point, what? What did I do wrong here? It's not 0. I screwed up somewhere. Where did I screw up? C is equal to minus a. AB minus d squared plus. I don't see where I screwed up. It looks like h is just 0 here. What am I talking about? Of course, h is 0 there.
Yeah, should be 0 everywhere now.
Yeah, so what am I... I'm trying to express it in local coordinates. That's what I want to do, but I'm doing it badly. I want to think about replacing... Yeah, what I'm trying to get at is if you... So if you were to pick coordinates at this point, some of which were along the surface, sort of in W0, and some of which were perpendicular to W0, and rewrite your function in terms of those orthogonal coordinates, you could figure out what kind of power it had. So how should we do that? On
So we need to figure out introduce another component t or some coordinate t that is orthogonal to the plane.
Would it be easiest on like one of the like non-diagonal planes?
Yeah, maybe we should do this red component. Okay, so this red component was a equals c equals 0, right? Well, then it's easy because we just have the remainder of the variables. Yeah. Maybe I should expand in. So, what am I trying to do? Yeah, so we just treat B and D as essentially constants. Right, so we're going to think about the polynomial ring in A, B, C, D as being functions that live on A, B equals 0, which is CD. Those are kind of like, those are the functions that live on this line, right? If you were to take the coordinate ring modulo the ideal AC, that's the polynomial ring CD. So you think of that as functions on the line, and then you sort of think about Taylor series expanding a function, but instead of treating just numbers as constants, you treat any function in C and D as constants. So that's because those are the sort of degrees of freedom along the red line, and then you have the degrees of freedom that are orthogonal to the red line, and those are A and B, and we're going to expand in those. That means looking at our polynomial and treating C and D as just constants. So if we do that, well, what have we got? We've got AB plus CD squared plus AB cubed plus CD cubed squared. So this is just a constant, and this is just a constant in this accounting. So that basically looks like AB squared plus AB cubed squared plus lower order terms. Okay, so this is kind of basically what we care about from the point of view of computing the RLCT, this function here. So it comes down to this. Now, as we move into the origin, we're actually sort of treating all the variables as things we actually have to account for. And so that'll change. The simple way to say it is that as we move from a sort of generic point onto this surface, along this surface, and then to the origin, we're steadily imposing more equations, right? From here to here, we're imposing A equals minus C. From here to here, we're putting A equals 0. And from here to here, we're putting the rest equal to 0. And those effectively are setting you can read those equations as conflating certain variables, right? A equals minus C, and then so on. And this will tend to increase the degree of the things that are left. And that's why it's becoming more degenerate. Yeah, that could be told in a better way, but that's the gist of why, if you were to expand this function in local coordinates at these different components, you would see more degenerate. Even though they're all where the function vanishes, you would see more degenerate behavior as you go along these components. And that's information that's in the polynomial, that's visible in the polynomial, that is implicit in the analytic form. Okay, that's all I wanted to say there. What do we want to do with the remainder of the time? Matt, did you want to continue with your interpretation of this picture, or a more general picture?
Yeah, I had a couple more observations.
Yeah, go ahead.
I'll take the speaker again.
Yep.
Okay, back to this other board. I wanted to just maybe my impression of what you just sort of talked about, Dan, is that this reduced parameter, this reduced form of the parameter, with this reduced algorithm that we talked about last time, is maybe quite important. Like maybe that's quite an important parameter within this level set, in general, and not just in this case where it's the origin, because I think it's probably the one where, in general, like the most constraints apply. So I'm saying even if the true parameter is not 0, I think this parameter that has the most 0 units possible is like an important version of that function, an important parameter that implements that function out of all of the parameters that implement that function.
Yeah, that makes sense. When we vary the true parameter away from 0 here, Spencer, what does it look like? In the projection, it's a bunch of lines, right?
Yes, yeah. It depends on how many components of the true parameter is 0. It almost depends on how reducible the true function is. And so it's like a bunch of lines, and then if the true function is completely irreducible, then I think it ends up just being a collection of points.
That's right.
Mm-hmm.
Yeah. Okay. Well, that's an interesting property of the reduced version of the parameter. Another thing I wanted to say is that just above this dotted line, where I've said that Watanabe's equivalent polynomial trick is like a heavier result than Sussman's equivalent polynomial. Sorry, not equivalent polynomial, reducibility conditions. So Sussman's reducibility conditions are like a pretty significant mathematical result, and the generalization, there's some work in the literature generalizing them to multi-layer networks, ReLU networks, and they kind of like saying something, you know, I don't think I would be able to come up with this, whereas I've been able to come up with the things in my thesis. So this is gives me a new level of, so Watanabe saying something even more than that, and that's giving me like a new level of respect for that equivalent polynomial result. Is like, to do the equivalent polynomial thing, you also have to solve the kind of the complex question of when parameters are irreducible versus not irreducible. That's my interpretation of this connection between these two approaches.
Yeah, that makes sense. In principle, elimination theory should let you kind of automate that process for other nonlinearities and so on. I mean, elimination theory is supposed to be the thing that would be able to take you from the equivalent polynomial itself, which doesn't explicitly contain this decomposition on the left-hand board. And in principle, there are algorithms. I don't understand them very well, but there are algorithms, sort of Buchberger-based algorithms for computing irreducible decompositions. So, you might imagine that in a good universe, you could take that equivalent polynomial, or you've written it as a sum of squares. In this case, 2 squares. So you take those f1 and f2, you stick them in singular, and you ask, okay, give me the irreducible decomposition, and maybe it spits out something like this, these reductions that you like in your picture. In practice, I don't know that that's actually feasible. So I guess I'm saying that.
Well, there's a lot of them.
Right. And yeah, that's right.
One of the things that doesn't really come up in this case is that like permutations factor into this. Permutations are the units, and also sign flips. So if you were to kind of normalize all of these components, and like do something like describe the set up to going and applying a permutation and assign flip to any parameter to get something else in the set, you would get something a little bit simpler. That's gonna, I imagine if you do this approach, all of that information, all of those permutations are within the kind of solution set of one of these polynomial. So singular is going to have to like wade through all of that, and you're going to get an exponential number of.
Yeah, you should be able to work
of the
equivariantly with respect to those symmetries, though. So you can just you can take the polynomial ring and the variables and move to a subring, which is the polynomials invariant to those symmetries, perhaps, and then try and do the algorithm there.
Cool.
Yeah, I don't know. I've never tried doing that, but
Okay. Okay, here's another observation, and I think Spencer already knew in his thesis and wrote that when you consider bias networks, you can't do this polynomial trick because you can't Taylor expand about something to do with when you have a bias in there and then you like set some of the parameters to 0, the bias remains, and then you have like tan h of a constant, and that is as a function of the constant, not a polynomial. So it leads to trouble. So what I've seen when I've done this in the more general case with biases is that when I construct these sets, these irreducible components of this 0 set, I can see there are components that correspond to something like where's my tablet? There are components then that correspond to something like this. The set of all parameters such that A equals tan h, A tan h bias 1 equals bias 3 if you augment the network we had before with a bias 1 here, bias 2 would be on the other node in the other hidden node, and then bias 3 is here. So this is not an algebraic constraint. And so the component that corresponds to this constraint is like like this or something. Instead of a plane, it's like a surface. Where this is like roughly the tan h shape. I don't know if it looks exactly like this, but you get the picture. It's not a linear component. It might be linear in some directions, and that's how I get my connectivity results. Every point on this plane is still piecewise linear connected, because you can kind of go to somewhere else and then go like this, and then go like this. So in 3 components, you can get to 2 different places on this nonlinear surface. But yeah, it's no longer algebraic. So that's just an observation. One other observation is that maybe like, if you wanted to get past this, one way that I think Spencer and I talked about briefly in the past is that you re-parametrize these biases to be with this like new bias parameter that corresponds to the arctan of the original bias parameter, then that would kind of cancel out with this tan h in all of the situations where you needed it to. And that would lead to that would kind of straighten out this linear surface. This re-parametrization would straighten out this nonlinear surface into a linear surface. So yeah, that's one other observation.
Oh, that's pretty interesting. Yeah, I hadn't seen this comment before. So yeah, okay, that means, I suppose, that the analytic to algebraic step is by no means assured unless you happen perhaps to have a good idea about how to re-parameterize. I mean, this is not, as you say, this is not an algebraic
Yeah, and I guess we're lucky that it's still pretty simple, nevertheless.
I have a question, probably for Dan. Might be a naive question. So if we the theorem about the desingularization and how to compute RLCT in terms of when we already have a normal crossing form does not require that the chart be themselves polynomial, as long as
Correct.
we get to a normal crossing form. So which means that we could it doesn't matter that we have so we have that the bias, introducing the bias, produce a non-polynomial constraint, but this is saying that if we have sufficient knowledge of what it looks like, what the constraints look like locally, then we can actually arctang it away, make it re-parametrize locally and make it normal crossing using a new transform. That's correct, right?
Right. Yeah, there's no theoretical problem. It's not like the theory cares that this particular constraint is not polynomial. It's just if you actually want to compute blowups and so on to determine what the RLCT is, this is an obstacle to doing that.
Oh, okay. So in this case, finding this particular re-parametrization, if it's indeed, I mean, I haven't gone and checked all the details, but I believe this will work. This will get rid of all of the non-polynomial parts of the constraints. If you're faced in general with an analytic set and you want to know its RLCT, it's something like, well, you bring me a re-parametrization and then we can talk. Whereas if you have a polynomial, if you have an algebraic variety, then you can kind of have methods, techniques, tools for finding the re-parametrization. So if that's the case, then maybe, but at least for 10H biased networks, we've brought the re-parametrization, and it's right here.
Yeah, I think this is a genuine advance.
And now we can take it from there.
Yeah, it's quite exciting. Let's.
So in particular,
try.
if we take our prior to be uniform on -1 to 1, this re-parametrization is always possible, isn't it? Because because the parameter is in the image of tanh. Yeah.
Mm-hmm. So as far as I know, the RLCT computations don't handle, the ones that are in the literature, they don't handle the bias case, and this is the reason. So it would be...
This is the reason, not that Watanabe ever says this is the reason, but surely this is why he didn't do it.
Yeah, I mean, I don't know if maybe in his head he's like, I don't care about the bias case really. It can't be that much harder than the unbiased case. And what I've shown is that, it's not that much harder than the unbiased case.
I don't think you very carefully avoid something by accident, but maybe.
Okay.
Even having said that, it does. I mean, it means that remark 7.6 is quite misleading, right, in the textbook, because it suggests a general method for going from analytic to algebraic. But yeah, I mean, of course, it's presuming that the coefficients, the FJWs in the notation there, are polynomials, which is not the case when you have biases. But it's then an open question whether this naive approach of just Taylor expanding the log density ratio and taking the coefficients, how often this actually produces algebraic functions. I mean, this is not a complicated example. One hidden layer 10H with biases, and already you have to be able to see
get it
this
with a single unit with biases.
Right.
Yeah.
So
a single unit is enough to get this.
So we should, I suppose, be a little scared that maybe it's just under our particular lamppost that you can get coefficients that are polynomials, and mean, maybe the bridge, maybe it's oversold, the link to algebraic geometry. I don't think that's true, but suppose somebody argued this and stood there and said, well, okay, in these 10 models you happen to have looked at and carefully avoided special cases where it doesn't work, you manage to find equivalent polynomials, but in almost all the other ones this is basically impossible, or it's like, a career's worth to figure out the equivalent polynomial and clever tricks in each one of the cases. So is algebraic geometry that useful, actually? I mean, certainly the resolution is useful, but in practice, to actually compute RLCTs, maybe you're just stuck.
I would say that I think it's okay, because look, I don't know how much harder finding the equivalent polynomial is compared to finding the reducibility conditions. That's something that I think would be good to talk about. Like, if this Watanabe step here is harder than the Sussman step, what is the kind of extra work? And in particular, does the Sussman step help? If you have the Sussman step, does it make it easier to do the Watanabe step? If so, then we have the Sussman step for various other models, various other activation functions, and they're normally pretty simple conditions, like the unit's input weight is 0, the unit's output weight is 0, or 2 units have the same input weight vector. And there are like a couple of other different types of conditions, but they're normally pretty simple constraints, and they're normally kind of linear or polynomial or something. So that
this comes down to the Null-Stellensatz for real analytic functions, unfortunately. So we have a nice picture of the 0 set of some function k, and then you can write down polynomials which cut that out, and then the question is, well, what does that say about your function and their relationship to those polynomials? That's what something called the Null-Stellensatz answers in the case of holomorphic functions, or polynomials. But it's a little, it's not obvious. I think it's a good question. Surely it must help somehow, knowing these decompositions from Sussman and the subsequent work. But it's not immediately obvious to me how to make use of it in this situation. But it's a good thing to follow up on. I'm going to have to go in a moment. I think this was a useful discussion. Does somebody want to put a cap on it, or have we said what we want to say? Did you have anything to add, Spencer?
That's everything for me.
No, I think we went through everything. Yeah.
Any other questions while we're on this topic?
Yeah, I have a question. I think I missed a bit the last line on this board, unless you re-parametrize with bias prime equals 10 inverse 10. Can you repeat that argument again?
Yeah, sure. So, sorry about the background noise. If you make this re-parametrization, then this constraint that you get in the biased case becomes your new parameter is this bias prime. So this constraint becomes maybe I've got the -1 in the wrong spot or something. But anyway, I want the constraint to become a bias prime equals. Here's the problem. Don't do the re-parametrization for the output weight, and so that this doesn't become tan h inverse, which is also not right. Anyway, so I want the constraint to become this from this, and if you just think of this basically as the bias parameter, that's what. So I think the -1 should actually be on the other side of this re-parametrization equation. Sorry, I would say that I didn't really answer your question so much as just stumble through that. Is that any clearer, or should I start again?
It's not any clearer, but I think maybe I'll stare at it. I don't want to hold us for too long.
Okay, I can try again on the next board. if there's interest.
Yeah, let's do it.
Maybe we can let people go.
Okay. Yeah, if anyone doesn't want to hang around for this, I think it's going to be not that much more than what's already been said. So let's consider a single unit network with a bias. So I'm going to call this A, B, and C. And so the function is f of x is equal to A tan h bx plus c. Now, the conditions under which this is equal to, oh wait, no, I have to have, sorry, a bias here as well, d.
Right.
What are the conditions under which this equals 0? We don't have an equivalent polynomial approach, so we have to go with the reducibility approach, but it's okay because it's so simple. Clearly, either, clearly we need A tan h bx plus c equals minus d. A couple of ways you could do this. It's simple if d is equal to 0, then you need, you could just make a equals 0, b equals 0, and c equals 0, and that would be fine. Let me say that again, actually. You make a equals 0 or make b equals c equals 0.
Right.
In either of these cases, a tan h bx plus c is going to be 0.
Yep.
The interesting case, I'm not going to be exhaustive here, like a more careful analysis would look at all of the cases, but the interesting one is when b is equal to 0. And now the constraint that remains is a tan h c equals minus d.
Yep.
This, it works for any a, c, and d that meet this constraint. This gives you a surface in the parameter space. And it's a non-linear surface because of the tan h.
Yep.
But if you start from the top with, instead of c, if you start with tan h inverse of c, and here you have tan h inverse of c. This is, I'm going to call c prime. So here you have c prime in, sorry.
Right, I see.
No, I'm getting backwards again, aren't I? We have c here.
So you re-parameterize the C to get rid of the non-algebraicity, right? Is that what you're doing?
Exactly, that's the idea, yeah. And I just have to make sure I get it the right way around. But what I want to do is end up with a tan h of,
okay.
yeah, tan h minus 1 of our new parameter equals minus d, and then that is just a times our parameter equals minus d. And now that is algebraic again. Not linear, but at least it's a polynomial.
Okay, cool. Thanks. Yeah, now it's clear. Thank you.
Okay, yeah. Okay, that's all for me.
Did you make a claim that this you can do this for other larger networks as well?
Yep. Because I don't know about deeper networks.
Yeah, single layer you can. Right? You can just repeat this thing, right? So, but not for deep. Okay, I guess deeper ones we don't really talk about here. No.
Well, I would still have to think about deep networks, but I would be, I wouldn't be surprised if this works because I think deep networks, the motivation I have, like, or the justification I have in my head for focusing first on the single layer case, like I'm kind of confident that there's a good chance it'll generalize to the, with suitable modifications to the multi-layer case, because you can kind of decompose these things by layer, treat one layer at a time, reduce that layer as if it was a single hidden layer network, and then move on to the next layer and reduce that layer where its input is now coming from the first reduced layer, and just keep moving through. And so, yeah, the sort of, I think the single layer is like the hard part.
Yeah. So how does this thing help us get the equivalent polynomial in the bias case? Was there a claim for that too? So now you got this A prime
equivalent polynomial, not sure, but zero set we can get. So that's the question of, we've got part of the equivalent polynomial. We have it zero set, but we don't know what the rest is.
That is actually part of my,
Sorry, did I miss something? I thought Dan was saying that we could kind of apply SLT to the bias case because of this kind of re-parametrization.
Well, I was saying that not having it is an immediate obstacle.
Right.
Once we have it, it's not like we're finished, perhaps. But yeah, I guess there's several things people may want to say and discuss. Let me just insert here, though, that I think actually one of the key reasons to be interested in the Sussman point of view and the point of view that Matt's spent a lot of time learning is that it probably gives you more courage to approach the deeper case. Whereas if you just look at the deeper network case purely from the equivalent polynomial point of view, it looks pretty intimidating, to be honest, right? It's not easy to get the equivalent polynomial, even for the one layer case. And I think it will be important to have the intuition to start from maybe tackling the deeper case via Sussman style approach is actually the right place to start, and then that will guide you on doing the harder work.
Yeah, I would kind of speculate that if someone did Spencer's thesis project and then did my thesis project, and then they could maybe like intuit the equivalent polynomial for a multi-layer network or something like that. They could just guess it and check it rather than having to derive it or something.
Cool.
Well, don't go away, Matt. Stay. Do a PhD. And there you go. I know you just want to keep doing this stuff.
No, Spencer should do my project.
That too. You can both do each other's projects. Okay, on that note...
You were going to say something, Edmund?
Yeah, Edmund, go ahead.
Yeah, I have a question, and I don't know if it is a long question. So my question is, for example, if we manage to find a re-parametrization that get rid of so a change of basis, a change of coordinates that get rid of this bias problem and makes it possible to get an equivalent and make it possible to find an equivalent polynomial in the new coordinate, but the change of coordinate itself is an analytic transform. That is still okay, right? That we will get the same RLCT. Am I missing?
Yeah, that's
is the logic flawed here? Okay, cool. That's what I want to check. Yeah.
Yeah.
That's what I wanted to check.
Any other questions or comments? Okay, maybe that's a good place to wrap up today. Thanks. That was really productive, I think. So next week there'll be a more lecture style. I'll give a bit of an introduction to some basic information theory topics. The ad for that is in the Discord. And maybe we should spend maybe 10-15 minutes next time with a few brief self-introductions, seeing as we have some new members and not all of us know each other very well anymore. It would be good to just briefly introduce ourselves and welcome the new members of the group that way. Okay, thanks everyone. See you next week.